Let's continue our discussion of voting systems. And in this lecture, we're going to look at the idea of head-to-head comparisons in elections. So what exactly am I referring to when I talk about the idea of head-to-head comparisons? Well, in our previous couple of lectures, we defined the idea of preference rankings existing for voters. And if the preference rankings of voters are known, then we actually have all the information we need to determine the outcome of an election that takes place between any two candidates. So head-to-head in this instance literally means you only consider two candidates and you determine if those two candidates were running against each other, who would win the election. And we then take these preference rankings, and in principle, we can determine the outcome of every possible pairing of candidates. So if we had three candidates, A, B, and C, then we could look at what would happen if A and B ran against each other. We could look at what would happen if A and C ran against each other, and we could look at what would happen if B and C ran against each other. With the preference rankings, the outcome of each of those elections would be known. And so when we have this kind of election, in principle, it's a plurality election, but there are only two candidates. So typically in that instance, there will either be a tie or there'll be a majority. There's not going to be such a thing as someone winning with a plurality of less than 50% of the votes. But this situation we refer to as head-to-head comparisons. So it's easy enough to run the numbers on this. An example that we looked at in the previous section, we have this committee of 5 people voting for a new chair. And so, again, we have our rankings here. So the first column, this just indicates to us the ranking with Coleman first, Horowitz second, and Taylor third. There was one person who had that specific preference ranking. Ranking with Horowitz first, Coleman second, and Taylor third, there are 2 people with that specific preference ranking. So if I want to know who would win in a head-to-head comparison between Coleman and Horowitz, any information on Taylor becomes obsolete. All I'm doing is saying, okay, for the first preference ranking, if in this preference ranking, the person had to pick a candidate, would they vote for Coleman or Horowitz? And in this instance, because Coleman is ranked higher or better than Horowitz, the person would vote for Coleman. In the next preference ranking, this preference ranking corresponds to a profile who would vote for Horowitz rather than Coleman. And how many people had this specific preference ranking? 2 of them. Now, the first 2 cases here were simple because they dealt with rank 1 and rank 2. But now we're looking at a ranking profile where Taylor had been ranked first. But of the 2 remaining choices, Coleman was ranked better than Horowitz. So this person would vote for Coleman over Horowitz. So it's another vote for Coleman. And in the last column, this person ranked Horowitz better than Coleman. So this person would vote for Horowitz. And so in this head-to-head comparison, Coleman receives 2 votes, Horowitz receives 3 votes. And so Horowitz would win the head-to-head comparison in this particular election. Now, we could do the same thing. In fact, we're going to do the same thing for every other possible pairing. So say we want to determine who would win between Coleman and Taylor. So now Horowitz becomes obsolete. We're just going to count votes for Coleman and votes for Taylor. In the first preference ranking, that one person with that preference ranking would vote for Coleman. In the next column, Coleman again has a better ranking than Taylor. So those two people would vote for Coleman. And then if we look at our third column, here this person ranked Taylor first, Coleman second. So that's one vote for Taylor. And then the last column again, Taylor ranked better than Coleman, so one vote for Taylor. But that tells us if this were the election being held, then Coleman, in this case, wins the head-to-head comparison. And again, there's one more head-to-head comparison that we could consider. If Horowitz and Taylor ran against each other, so that would make Coleman obsolete in the comparison. We would just count votes for Horowitz or votes for Taylor. So let's just run through. Here, Horowitz is ranked better. In the next one, Horowitz is ranked better. In the third column, Taylor is ranked better. In the last column, Taylor is ranked better. So from the first column, Horowitz would get one vote. From the second column, Horowitz would get 2 votes. And then third column, Taylor would get a vote. Fourth column, Taylor would get a vote. And so Horowitz, in this case, wins the head-to-head comparison. Now, let's take a look at the situation here. If Horowitz faces off against any other candidate, right? If Horowitz runs against Taylor, Horowitz wins. Earlier, we had an example, Horowitz running against Coleman, Horowitz wins. Those are the only 2 pairings that include Horowitz. Horowitz versus Coleman or Horowitz versus Taylor, and in both of those, Horowitz comes out ahead. So if Horowitz is in a head-to-head comparison with another candidate, Horowitz in this example wins the election, and we have special terminology for this. In this case, Horowitz is our Condorcet winner. Condorcet will always be capitalized because it's referring to a last name. It's a definition named after a person with the last name Condorcet. So a Condorcet winner is a candidate who, if that candidate shows up in any head-to-head comparison, they always win the head-to-head comparison, no matter who the other candidate is. So if they always win, we call them the Condorcet winner. We could also have a situation where that candidate either wins or maybe sometimes ties, but never loses. If the candidate always wins or ties, then we refer to them as a weak Condorcet winner. So this just is some extra terminology to emphasize someone can be a strict winner. So if they're in any head-to-head pairing, they're always going to win. Or someone can be a weak Condorcet winner, which essentially means they never lose. They sometimes win, they sometimes tie, but they never lose a head-to-head comparison. So Condorcet winner versus weak Condorcet winner. And there are many people who argue that the Condorcet winner should always be the winner of an election. So they say, forget about plurality, forget about having runoff elections, forget about border counts. Find a way of determining who the Condorcet winner is, because that is the person, it doesn't matter who they run against, they will win that election. So it seems like a reasonable way to define an election winner. The problem is, no election comes with a guarantee of a Condorcet winner. It's entirely possible that the preference rankings that people have do not result in an election having a clear Condorcet winner. So it's a nice idea to say, oh, we should always have the Condorcet winner be the winner of the election, but sometimes that candidate just does not exist. In fact, we have a little example here, just illustrating how there may not be a Condorcet winner. So we're going to look at the head-to-head comparisons. We have 3 candidates, so we can run the election of candidate A against candidate B, candidate A against candidate C, and finally candidate B versus candidate C. So if A runs against B, in that instance, C's information is not relevant, right? So A would get a vote from the first profile, B would get a vote from the second profile, A would again get a vote from the third preference ranking profile. So A has 2 votes versus B having 1 vote. A wins this election. What about A versus C? So that means B is now obsolete. First profile corresponds to A winning. Second and third profile correspond to C winning because that's where C is ranked better. So now A gets 1 vote, C gets 2 votes, and so C wins. And if we look at the last head-to-head matchup, B versus C, so A is now irrelevant. In the first pairing, B has the better rank. In the second profile, B again has the better rank. And in the last profile, C has the better rank. So B would get 2 votes, C would get 1 vote, B wins. So you can see there is no candidate that can claim they always win the election. If A runs against B, A would win. But if A runs against C, A would lose. Same thing. If B runs against A, B would lose, but B would win against C. There's no candidate here that always triumphs. So no candidate wins all of their matchups. And that by definition means there is no Condorcet winner. Here's the other problem we have just from a real world perspective. We do not always have all the preference rankings for voters. A typical election plays out in such a way that people go into the booth and they participate in a plurality election, so we only know who their first choice is. And then sometimes there's a runoff election, and the runoff election would reveal to us, for the people who didn't have their first choice make it to the runoff, who they are switching to. So that tells us kind of who their second choice is. So in a typical system, the best we could figure out from an election without making extra assumptions is first choices and maybe second choices. And there could be a lot more candidates than that. So if we don't know the full preference rankings, then we have to develop a mathematical model if we want to use that information. So mathematical modeling here refers to a way of handling real-life problems by deducing or hypothesizing a specific mathematical structure. So it's a way of hypothesizing about what the later on preference rankings of candidates could be. And we're not going to delve into that in this class. Just know that this is a concept that does get used in practice, especially in situations where we would like to have information about a Condorcet winner, but the full preference rankings just are not available to us from the data at hand. And often people have different ways of constructing these models. Generally, we consider these models reliable if people develop slightly different models, but even though they their models are different, they still get pretty consistent results. So maybe they don't get the exact same vote totals, but they do predict the same Condorcet winner using different methodology. Now, we've now talked about 3 different methods of voting, or technically 4, because we could just have a plurality election, or we could have a plurality with a runoff. We could do a border count, or we could calculate a Condorcet winner. For border counts and for Condorcet winners, we need full preference rankings. Plurality and plurality plus runoff, we don't need that, but if we have it, we know how those election outcomes would turn out. The interesting thing is, even if an election has a Condorcet winner, there is no guarantee that the Condorcet winner would correspond to the person who would win in a runoff following a plurality election. There's also no guarantee that the Condorcet winner is the same as the border count winner. So there are real-life situations where all 3 of these methods would result in a different winner of an election. Part of what's going on is we sometimes talk about a candidate acting as a spoiler for someone else. So what could be happening is the Condorcet winner may be someone who consistently gets ranked second by everyone, but is never ranked first and never ranked last. Or maybe even someone who's consistently ranked third. They could easily end up being the Condorcet winner if there were, say, 10 candidates, but there's a lot of change between who ends up in first and second place, but there's a lot of consistency about who ends up in third place. But if that person was consistently ending up in third place, there's a solid chance that they don't make the runoff election and therefore would not win. So these methods don't have any guarantee of agreeing on the outcome. Now, the other problem with the Condorcet winner is that it can be pretty tedious to make this determination. The examples we've done in this lecture look at having only 3 candidates. And if there are 3 candidates, there are 3 head-to-head matchups. But there's a formula to actually determine how many head-to-head comparisons there are. If there are C candidates, then the number of head-to-head comparisons is given by C times C minus 1 divided by 2. So if there were 4 candidates, then 4 times 3 divided by 2 would mean there are 6 head-to-head comparisons if we have 4 candidates. If there were 5 candidates, it would be 5 times 4 divided by 2. So here there would be 10 head-to-head comparisons. And the number of matchups grows much faster than the number of candidates. In fact, if you got to an election with 10 candidates, you would end up with 45 head-to-head matchups. So it just blows up pretty quickly, and it becomes impractical to run and evaluate all the head comparisons. So what do we do in this situation? Well, the typical procedure involves identifying 2 strong candidates. You can just look at the 2 top scorers from a plurality election, or you can implement the full border method and take the 2 candidates with the highest border counts. That gives you 2 starting candidates, and you run a head-to-head comparison between those 2 candidates and determine who the winner is. You then take the winner from that strong matchup, and you compare that candidate to all of the other candidates. Now remember, there are C candidates in total. 2 of them were just involved in a matchup. So the remaining number of candidates after that matchup is C minus 2. So the winner from that first matchup gets compared to every other candidate one by one in a head-to-head comparison. What this means is if that person wins each of those elections, they are the Condorcet winner. But if you go through this procedure and along the way you find a new winner, someone different than the original winner who wins the head-to-head matchup, then you start from scratch and compare that person again to all the other C-2 candidates. And either you're going to have that person now win every matchup, or you're going to find a new winner along the way again. If you find a new winner consistently, you're always going to go back to the start and run head-to-head comparisons for that person against everyone else. And you keep on doing this until you find a candidate who wins every head-to-head matchup they're in. Again, this will only help you if there is a Condorcet winner. Otherwise, you're going to get stuck in an infinite loop. If you're ever going through this process and you at some point get back to a winner you've previously had, then that will tell you to stop, because you're just going to cycle through the same set of elections again. So if there is a Condorcet winner, this will help you find that candidate a lot faster than having to do every single possible head-to-head comparison. In fact, this requires that you do between C-1 and 2 C-3 head-to-head comparisons. What does this look like? If we have 10 candidates, remember, if we do every possible head-to-head, there are 45 head-to-head matchups. But this tells us C-1 in this case would be 9, and 2 times C, what I see is 10. 2 times C-3 would be 17. So this tells us rather than having to do 45 head-to-head matchups, we'll do somewhere between 9 and 17 before we find the winner. So we've more than cut the work in half. It really has the potential to speed things up a lot to do this cyclical procedure. And I'm pretty sure we'll look at an example similar to this in our next live session on Thursday, June 4th. The other question here is, getting into this whole process is only sensible if you actually know that there is a Condorcet winner. Like, you don't want to go through all this work if there isn't a Condorcet winner that's going to emerge victorious. So one way of doing this is by creating a visual display of the preference rankings. And there will be a specific ordering of candidates with a desirable property, in this case being single-peaked. Now, that word of it on its own is not that meaningful. I think the best way to understand this is to look at an illustration. And I can illustrate it with a 4-candidate election, but it easily generalizes from there. So say we have 4 candidates, A, B, C, and D, and every voter is asked to give their preference ranking of the candidates. We then make a graph by putting the candidates on the horizontal axis and plotting their rankings on the vertical axis. And if we're able to create these graphs of the preference rankings, and every single graph is single-peaked, then there is a Condorcet winner. On the other hand, if you find a graph with multiple peaks, it actually doesn't mean that there isn't a Condorcet winner. It just means you can't guarantee that there is a Condorcet winner. So single-peakedness guarantees you have a Condorcet winner. Lack of single-peakedness is not all that informative. What does single-peakedness look like? Well, say we have these candidates and we get three different preference rankings. So this first ranking corresponds to someone who ranked D first, A second, B third, and C fourth. So we have three different preference rankings for the candidates. Now, the question at hand is, can we find a way of ordering the candidates on our horizontal axis so that if we plot this preference ranking, so in this first one, candidate C was ranked fourth, right? So C, I put opposite being ranked fourth. Candidate A was ranked second. Candidate B was ranked third. And finally, candidate D was ranked first. So if I do this for a specific order, and in this case, I'm looking at the order C, D, A, B, and I connect those dots, and I end up with a graph that has a single peak. In other words, if I go to the candidate that has the best rank, then that is the peak of the graph. There's no secondary peak. All three of the plots shown here have a single peak. In the second graph, the peak happens to be, on the edge of the graph, but if you follow the graph from there, it just traces downwards. And here's another one. Candidate A has a peak and the graph descends in both directions. So I will not expect you to just know what the ordering is that you should look at. What we're talking about here is what we sometimes in mathematics call an existence result. We are saying it is possible to confirm the existence of a Condorcet winner if we can find a way of ordering the candidates so that we can make single peak graphs. What does it look like if a graph is not single peaked? Let's say there was a fourth preference ranking of these candidates, and I again use the same ordering and I plot the preference rankings. Here's an example of a graph that it decreases, then goes up again, then goes down again. This graph has two peaks. And so, at least corresponding to this specific ordering, this ordering does not, it no longer tells us that there is a Condorcet winner because we draw our preference ranking graphs and we find one that is two peaked. The moment that happens, that ordering is not informative. Now, you could go and try to reorder the candidates. In this case, if I just switched up the candidates, if I ended up putting C first, and then A, and then D, and then B, sorry, it should, best rank should be at the top. And I now plot this. In this preference ranking, C was ranked first, A was ranked second, D third, B fourth. So I now have a single peaked line. Have I solved the problem? No, because I've changed the ordering. So I have to go and check what's the effect on every other preference ranking graph, because I need to find an ordering where every one of those graphs only has a single peak. So it's not about finding a ordering for a different ordering for every preference ranking. It's about being able to find a ordering of candidates that holds for every preference ranking that voters have. But if you can find that, it guarantees the existence of a Condorcet winner. So I know there's a lot to take away from that, in that this is a bit more of a conceptual idea. I think even though it can be tedious, sometimes it is a bit more simple just running all the head-to-head comparisons. In fact, if you are good at working with a spreadsheet in Excel, you can typically do all the head-to-head matchups in Excel without a whole lot of difficulty. But if you are in a really large election, there is an argument to be made for determining whether there is a Condorcet winner before you do all the work. Because typically there will be far fewer ranking profiles than there are votes that you have to account for. So it all depends on which is less work. Now, to wrap up here, I'm going to refer you to page 41 in Mathematics Beyond the Numbers, because it also talks about what about situations where there is no Condorcet winner. So someone may have an election and decide beforehand they want the Condorcet winner to be the election of the winner, to be the winner of the election. But there's no guarantee that any election will have a Condorcet winner. So they therefore need to have a backup procedure in case no Condorcet winner emerges. And we just simply refer to this as a Condorcet completion process. So it's the backup procedure, if there is no Condorcet winner, that we follow to determine who the election of the winner is. And what you'll see on page 41 is it talks you through. Sometimes people will say, okay, if there's no Condorcet winner, our backup method will be the border count. Or maybe a backup method will be to eliminate the weakest candidate and rerun the Condorcet election, see who comes out ahead if we just drop out the weakest candidate using, say, a plurality criteria. There are a lot of different ways you can approach it, as long as you recognize that if you're running a Condorcet winner type election, a backup procedure needs to be in place. Otherwise, you could end up in this unfortunate situation of not having an election winner.